All right, in this video we're going to talk a little bit about the center of mass. So let's say I have an XY coordinate system. I have three masses sitting in that plane, and I'm trying to figure out where the center of mass is. In the notes, what we talk about is the flocking of birds and how your eye is sort of trained to the center of that flocking of birds. We can mathematically calculate where the center of mass would be for these objects. So let's say the first one is located at location R1. The second is located at R2, and the third is located at R3. To calculate where the center of mass is, we're going to take the weighted average of these positions, weighted by the masses. So the definition of the center of mass, the position of the center of mass, is the weighted average, the sum of m1 R1 plus m2 R2 plus m3 R3 divided by the total mass, m1 plus m2 plus m3. And so in general, what you're going to have is that the center of mass is the sum of each individual mass times each individual location vector divided by the total mass. So this is just a simple mathematical calculation. What we'll find is that the center of mass is maybe roughly about here. It depends on how massive each of these objects actually is. What's really interesting is when we start to track how the center of mass moves. So if we want to know about the velocity of the center of mass, that's simply the derivative, the time derivative of the center of mass position. And so when we go and do that calculation, so long as the masses are not changing, right, we'll have 1 over the total mass out front times the time derivative of the sum of each of the contributions to the center of mass. So m1 times r1 plus m2 times r2 plus m3 times r3, and so on. As I said, if the masses are not changing, what you'll have is 1 over the total mass times m1 times the velocity of object 1 plus m2 times the velocity of object 2 times m3 times the velocity of object 3, and so on. Each of these is the individual momenta of the particles as they're moving, right? So if they have their own velocity vectors, let's say v1, v2, and v3, these products are just the momentum of each of those objects. So what we have now is that this is 1 over the total mass times the sum of each of the individual momenta, which we know to be the total momentum of the system. So 1 over the total mass times the total momentum vector. And so this is all equal to the velocity of the center of mass. So we have a description for the velocity of the center of mass in terms of the individual parts, but also the momentum of the total system, which is that the total momentum of a system of objects is equal to the total mass of that system times the velocity of the center of mass. So going back and thinking about how we can track this momentum vector, the total momentum vector, it tells us a little bit about how this collection of objects is moving collectively. Not how they're moving around the center of mass, but how the center of mass itself is moving.